another session. So, Dr. Singh, actually, I will basically I'm taking this session from my home.
Yes,
And,
sir.
so, in between, let's say I can take a break, 1 or 2 minutes, right? I hope.
No issue. No issue, sir.
Yeah, actually, my kids online
Okay.
is going on. And sometimes they need help.
No problem, sir. Actually, sir, there are two sessions, so anytime you can take break. No issue,
No,
sir.
means no, I just 1 minute. Actually, I have to just go and
Okay.
check
No,
on the laptop and some technical
no
issue.
problem. No
Yeah.
problem. Sir, one more thing, sir. Your voice, mic voice is little low. Can you just increase the mic voice?
Okay. Now it is okay. Hello.
Uh, sir.
1 minute. I think.
Yes.
Uh, Hello. Now it is better.
Sir, slightly better, but not very high.
Now.
Yeah, I think, okay, that will be fine, I think, sir. Okay.
So I actually have increased
Hmm.
the volume to full. I guess. So okay. So let us.
Yeah, that's fine, sir.
Uh, okay. So basically I started a course on electric vehicles in IT Delhi 3 years back, and so regarding that, I have some material. I teach in the class regarding modeling of vehicle dynamics. Basically, and most of these things are available in my NPTEL MOOC course on electric vehicles. So it's 10 hours course and basic course. So if somebody misses this or something, you can go and look into it. So, okay, so I will cover the basic, and actually I want participants to be very interactive. Otherwise listening one way or even talking one way actually is no good for any interaction. Otherwise you can even listen to a YouTube lecture. But please interrupt me. I love to ask answer questions and interact because I also learn from the questions. So let it be a very interactive session. I request you to be, interrupt me anytime. Let it just be a informal session. It's not like I am speaking, you are listening. It's not like that. Just in a class, typical class where we just interact with the student and it's live. Let it be live. Uh, so for that, your support will be, you make it live and you ask question anywhere where you think. It can be discussion. It should not be like what you think, even you can ask something what is going on and where it is. So anything, let it be very informal. So I will switch off my video so that things. I think the voice can be better and
Yes, sir.
yeah. So I guess you are able to see my slides. Uh,
Yes, sir. We are able to see.
okay, so this is basically a online FDP on electric vehicles sponsored by the ATAL program of the government of India, and it is organized by NIRIST, and all of us are interacting under this umbrella. So, basically, as
So, sir, I'm sorry to interrupt you again. Sir, actually, the voice is still very low. Sir, are you having multiple mics like in other system also, sir?
one minute.
Seems like the mic is not coming from your headphone. Maybe it is coming from
So,
some. Yep.
I think I will. This MS team, I will just. Now it is better or something. Okay, let me. I think what happens now. Uh,
Sir, if you are using webcam, most probably the mic is coming from there also. In that case, it will be low instead of coming from your headset.
it's coming
Uh,
from where?
sir, are you using webcam? having mic.
Webcam is there, yeah.
Yeah, so sometimes there is inbuilt mic in the webcam also. So
So webcam anyway switched off, no?
okay, no, no,
So
the device mic may be activated, sir. You can go to the settings, sir. If possible, you can check which particular mic has been selected in your system, sir. If you go to three buttons there at the bottom near the present now,
hmm,
there is three button. If you click there, more options will be pop up.
okay, okay. So
So there microphone option is there. From there, you can check whether which particular mic has been selected, sir.
1 minute, I will just
Yes.
present. Actually, I will present now so that you can also check what I am doing.
Okay,
So
sir.
basically, so you are asking go to here this setting, right?
Yes.
So I
This
think
mic, yeah.
I think I am using the real tech only, right? I guess 1 minute.
Yes.
Uh, I just remove and I think this is real tech mic only, right? I guess.
Yes. Yeah, it seems okay, sir. But I don't know why it is very low.
Oh, oh.
I think now it's okay, sir.
Hello, is this better now? I don't know.
No, sir. Just earlier to that, sir, it was coming actually, sir. I don't know what happened exactly, but the
No.
sound was very clear just before that, sir.
Now,
Yeah, yeah, yeah. Now it's fine, very fine.
actually, I'm not using speaker now.
Okay.
So, so basically, so it is like uh, I'm not using one minute. Let me turn on my.
Hmm.
So I'm not using my headphone. It is just
Okay. Yeah,
so it is better.
but better compared to the first one, sir.
So it's just a desktop PC.
Okay,
Okay.
fine, fine.
Anyway, let's go on.
Okay,
uh,
fine.
uh, chalo, anyway. So as all of you know, basically. Uh, Actually, you will get a lot of noise from my surrounding. That's another problem.
Yeah, I think, sir, that will be okay. I think we can adjust that.
Yeah, because my kids will make a lot of noise about it. So,
Okay, no problem, sir. No problem.
so actually, so as all of you know, that we have two sessions. Basically, one is regarding modeling, and another session regarding simulation. So, uh, so let us go ahead with the modeling first. Uh, so I'll just come in a minute.
Okay, sir. Okay.
So basically, I'll be discussing this vehicle dynamics. Uh, So initially we'll just understand, the mechanical system. So electric vehicle comprises of a mechanical system and electrical system. So mechanical system is basically the wheels and the axle, the the gears and all that. That is all mechanical things. And even the design of the vehicle is equally important for EV kind of application. Then you have electromechanical system, which is a electric motor. So Dr. Singh, you can interrupt me if you think anything is right.
Yeah, yes, sure, sure.
So you have a mechanical system and you have electromechanical system, which is electrical machine, and then there is a lot of electrical system, right, from battery, power converter, and you can have DC-DC converters, DC-AC converters, and then they will be feeding the electrical power to the electrical machine. So this is the whole spectrum of things. So, but when you let's say you go to an industry, or you are you want to design your vehicle. So there is a very important thing which is called the design, vehicle dynamics design. So means you should be able to understand the different parameters related to mechanical system, and you should be able to put in your larger model. So it's very important part, and equally important part is the motor, then power converter, and the battery. So these all things need to be modeled. So I think in this talk we will talk about the modeling of mechanical system. But towards the end, if we have time, actually I teach a subject called electrical drives. So basically I can even discuss something about power converter and electrical machine. But this is a very important starting point, because this is generally missed by electrical people. Electrical, actually all of us are electrical, so electrical people are mostly good at modeling of battery, power converter machines, but the mechanical part is equally important. So a typical vehicle, all of us know that our we have 2-wheelers, 3-wheelers, and 4-wheelers. So one is let's say you have to drive your vehicle against some resistive forces. Like you may have air which is opposing you. Sometimes air can help you also. Then the resistance of the tire and the surface on which you are driving so the road conditions basically. You can also have gravity as a opposing force or a aiding force, depending on whether you're going up a flyover or up a hill, or you are coming down the hill or something. So it can be both positive and negative. So these kind of forces are very important, and that's why the design of the vehicle should be looked into. Secondly, the mass of the vehicle. So let's say we all know that our typical the vehicles what we have, even the older ones, like say Ambassador and all those things, are very heavy vehicles. Heavy vehicles means their body is actually made of iron or steel, or it's very rough, tough vehicle. But I'm not sure that kind of vehicle is suitable for EV application. Because the mass of the vehicle, will take a lot of energy for accelerating the system. So basically, there are there is something called system level design, and there is something called component level design. So system level design is a bigger picture, bird's eye view view of the system. So typically, let's say if somebody asks you, okay, what you are looking, so they will say always two things. Say actually my acceleration should be so good, such that I can accelerate from 0 to 100 km/h 5 seconds, 10 seconds. So that's how the generally the vehicles are, compared. So, so, so acceleration is important. Secondly, range. So range is a, is not a parameter in petrol-based vehicles, but that is important for an EV because let's say if you are using a battery electric vehicle, your only source of energy is battery, and so there is a limited amount of energy which is stored in the system. So range is a criteria. So let's say, but these are two conflicting basically thing, because let's say you have a battery with a certain amount of energy stored in it. Okay, so if you want very high performance, like high acceleration and all that, somewhere you're eating up your energy, and so you have to sacrifice on range. So these two are kind of conflicting thing. So acceleration means so acceleration means power, and range means energy. So so basically, typically we all know that battery stores energy. So energy defines the range kind of thing. But so energy defines range only when the power is a constant parameter. If power is not a constant parameter and it is very so the average power is quite high. So so it all depends on the average power. So if average power depends on what kind of acceleration you want. So if you want high acceleration and all that, your average power will go up and your energy draining becomes more and more. So that is the broad level. People have to think that okay, I am making an electric vehicle. So say you all of maybe hearing this terminology. It can go 350 km per charge, 200 kilometers, and for typically urban, 80 km per charge means once you charge the battery, it can go to 80 kilometers. But it's not. So there is a star always. So if somebody claims that there will be a star, so that star depends on that. You will tell that okay, don't fool yourself. 80 kilometer it can go only when your speed doesn't go about 25 kilometer per hour, and your acceleration is so all those are generally not told in the while claiming things. So this has to be read properly. So once you have the broad understanding of the system level, you go to component level. Component level means okay, depending on your range requirement, your energy is fixed. Let's say for a constant average power. So you will decide what the rating of the motor, rating of the IC engine in case it is a hybrid thing. Then rating of the power converter and the control system and all those things. So this all has to be after this first system level is done, you go to component level, and after that these all things has to be modeled. The battery, power converter, machine, mechanical system has to be modeled, and there will be a lot of iterations. Iterations means okay. So you have started with the load side, this requirement of the mechanical system, acceleration, range, and all that. It has come to the electrical side. So based how we can achieve this kind of power. So what machine we should use? What is the? So if you use the machine, actually, just say if you have a 10 kilowatt machine or a 50 kilowatt machine. So from this side, one thing is the power rating. But another important thing is the power is not is not a single entity. Power is a let's say if you understand in terms, it's a product of voltage into current in electrical domain. It is equal to torque into angular velocity in mechanical domain, rotational system, and in a linear system is called force into velocity. So it is not an independent thing, right? So let's say if you want to run the vehicle at certain speed. So that speed is somewhere related to the the speed of the motor. The speed of the vehicle and the speed of the motor are related. So let's say if your motor is a high-speed motor, generally we use let's say high-speed motor, 1500 RPM, 3000 RPM motor. But your vehicle actually, if you see the speed, the rotational speed of the rotor, the typically car or something, it is in few hundred of RPM, 200 rpm, 300 rpm. So there is a, there is a gear ratio. So there need to be a gear, because if you're using a 3000 rpm motor and you have to operate maximum 300 rpm of the rotor wheels, you need to have a gear of 1:10. Okay, so that is done. Now, so for the power, if you have fixed the speed at let's say 3000 rpm, so the power divided by that omega will tell you the torque available to you. Now, what is the torque? So so speed we have taken care. What is this importance of this torque? So this torque is equally important. So if you have a gear ratio, so then if you in a gear, let's say in a transformer, we have voltage and current on the primary, voltage and current on the secondary. It can be step up, step down. Like similarly in mechanical system, the gear is a step down and step down, step up and step down. Piece of equipment. So if you have high speed on one side and low speed on another side, it will also happen that the higher side speed will have lower torque and the lower side speed will have higher torque. So that is beneficial in this case, because so we are looking for 300 rpm on the rotor actual vehicle wheels, and we are using 3000 rpm. So for that same power, torque will be 10 times more on the wheels. So what we are giving on the motor side. So, and that torque is equally important, because that is a force what you are applying to the wheels. So, and moving forward, let's say when you decide the torque and basically torque of the motor and speed of the motor, somehow you have also decided, you have to decide what is the voltage rating of the motor and the current rating of the motor. So, and so as all of you know that we are using battery for electric vehicles. So, the battery voltage is a limitation. Limitation means, let's say all of us wants to work on a battery of 24 volts, 48 volts, 96 volts, 72 volts. We don't want to increase it too high, because there are safety standards which doesn't allow, so they allow currents up to 200 amps and all that, even more than that. But on the voltage side, HEC is more constrained. So again, now you have a 10 kilowatt motor, and if you are using a 100 volts battery, let's say 96 volt battery, and the DC link is 100. So even in that case, you have to pump current of 100 amps. So 100 volts into 100 amps is 10 kilowatt. And imagine if you have to go for 50 kilowatt and 100 kilowatt motor, what is used in a typical car, a high performance car. So there you need to increase the DC link voltage to 300 and 500, so that currents are still under some kind of under 200 amps and all that. So that's another. So these are all things has to be designed. It's not just one parameter. So as I already told, acceleration is depending on the torque rating. Torque speed is again power rating, because torque into torque speed is power. Range is basically a function of energy, which is depending on the battery capacity. So modeling, when you go for modeling, there are two types of modeling. It's basically longitudinal and lateral. So we generally do longitudinal modeling because we are not using multi-wheel driven vehicles. So all of you know there is a possibility that so it's possible to use only one motor, right, for driving the whole vehicle. But there is another possibility now. You might have hearing that multiple motors are attached to multiple wheels, and so each wheel is driven by individual motors. So in that case, now the lateral vehicle dynamics comes to the picture, and it is quite complex. And but it's complex, but it gives the flexibility that no petrol-based car can give. So it takes the electric vehicle to a next level, even better than petrol-based vehicles. So like the cars like BMW i3 or Tesla and all that, why they are very popular? It's not because of only electric. the performance, the kind of controllability you have in those vehicles are enormous, enormous. You have all the flexibility. All the four wheels have four motors, and they are controlled in complex control systems. You can park your vehicle just shifting your car by 90 degrees. And all of you know that the engine has the engine doesn't have a smooth speed control, but electric motor can have a very precise speed control at very nice dynamics. So electric motor control based vehicle will be of very good. So that's another why people are looking for this kind of vehicle. So I basically have to keep track of the time also. So tractive effort. So what kind of force we require to drive a vehicle? So these are actually some basic things, but it's important. As we know that if you want to drive a vehicle at certain velocity and you're going uphill at certain angle theta, you have to overcome the rolling resistance, aerodynamic drag, slope or the gradient, and most importantly, actually you want to go at certain acceleration. That is your desire. But other things are opposing. It can sometimes aid. Also, gravity can aid, and that is very important because negative gradient you can use for charging your battery. So typically, if you see how these forces are calculated. So let's say a car is going uphill at angle theta, you want a tractive effort. You have to calculate what the tractive effort required to drive the vehicle. So you have to overcome this rolling resistance, which is the friction of the tires, the gradient force, the aerodynamic force. Aerodynamic force is the force due to the air. So if you go at higher speeds, right? So if your design of the vehicle is not aerodynamic in shape, there will be a lot of drag. So you might have all seen the aeroplanes and the high-speed trains have very nice aerodynamic shape near the engine. It has to be, otherwise like a lot of drag will be there. So the aerodynamic drags are basically two types. One is called shape drag and skin drag. So shape drag, all of you can understand. If you say very bad shape system, so it will take up a lot of energy to overcome that. Skin friction is another thing. Basically, so when you move in the road, so you are pushing the air at certain speed, but the air which is adjacent to your vehicle will be at zero speed. So there will be friction between molecules. So between two air molecules, one is stationary, one is moving. So this is skid drag. This is equally important. Basically, if you see a good electric vehicle, it will not have ducts and all that. It will not have a outside mirror or something. It's a mirror we have in our vehicle, both side mirrors which is protruding outside, and all those things will be avoided. So this drag is a function of all kind of frontal area, means the area which is just facing the front. So and all kind of protrusions, side mirrors, ducts, air passages, spoilers. Actually, these all will be missing. Air density. So air density is important function. So the air densities are different at the ground level and at the hills and during summer and winter. So velocity of vehicle, velocity of the air, if we are supposing it. So this is a formula for aerodynamic drag. It's a function of rho, which is density of the air. CD is aerodynamic drag coefficient. Basically, this is a parameter which you can calculate or you can test and get it once your vehicle is designed. So there are certain tests which are done to find out the CD for your vehicle. and this velocity of the wheel and velocity of the air. So if the air is opposing, so you have to you have to give more force. But if the air is helping you, let's say air is coming from behind, then the force will be actually lesser than what is normally required. So typically this drag coefficient is the range of from 0.1 to 1.5 or something. Uh, oh, hello. So basically, the first electric vehicle which was launched globally was General Motors EV1. So that was launched in 1996, and it was very good vehicle actually. So I am actually it was the vehicle has come too much ahead of the times. 1996 it came, and very good design, very good. They have used induction machine drive with IGBT converters, and very good design of the vehicle. But it has come too much ahead of the time because there's no charging infrastructure and all that. So that's why it was not able to pick up. Now the focus of the global countries is different, and you have better infrastructure. So and people are more aware of. So that at that time, even the design was so good that it was 0.19. So this will basically help you to understand what is CD. So so you can understand, if you design, kind of. So this is normally a normal kind of open van, all these things. But this design, this wedge-shaped design this is the design of the EV1, what I was talking about. So it was quite good, like it was. And then this is still, you can see that it is more better than this. And here you can see that even the tires are not outside. So tire is inside. You cannot see the full tire. So this is even better design. And this back side is equally important. So when the air comes from back from the front, right, it goes and it should find a very easy path. Otherwise, not only you have a high pressure area here, you have some kind of a low pressure area at the back side. So in these vehicles, it will be there. In this, it will not be there. It will be smoothly goes out. This is very good design. So actually, it can be further improved, and you can see that these trucks and all those buses and all those have a very horrible CD because they have because they are either running through petrol or through electricity. But if this has to be electric, then I think the design of the buses has to be equally changed. The normal buses, if you use actually, they will the design and the weight of the buses will heat up all the battery energy. So this so air density actually it is different at different basically climate. Let's say it is very high at in cold countries, and it is low at some hot countries. So once you know the force, actually you should know the power, and then there is. So it's a very heavy. So it's a heavy function of the power. For determining is a heavy function of speed, Q function. So this is very tricky, so this force becomes very predominant at very high speeds. So let's say if a Tesla vehicle is running at 200 km/h, and the aerodynamic force is enormous. And if the CD is not in very good, if CD is high, it will eat a lot of energy. So we'll see how it affects in some kind of simulations. So here actually some example is given. So let's say if you're running at 100 km/h, and these are the the mechanical CD and frontal area. Let's say energy available is only 10 kWh and energy density is okay. So if there's no wind, you can go to 125 km/h, and if there's opposing wind of 10 km/h, then you can go only 100 km around. So So basically, so this kind of winds are normal in some, some places, and the CD is very important. And another thing is, like I don't know, it's a heavy function of speed. So let's say the power required when you run at 120 km/h versus the power required at 100 km/h, it will vary as a function of cube. So you require almost, just you want to drive the vehicle with additional 20 km/h, but the power required is almost 72% more. So, and energy wise, energy is a square function, so it is 150% more energy will be required. Just you want to increase the speed from 100 to 120 with all other parameters same. So that's why this CD coefficient and all these things are important. So roller resistance force. This is basically due to the friction between the tire and the road, and it also involves the weight of the vehicle. So all of us know that like when you drive on a very good road, your friction will be less, and but if you drive on a basically a muddy road or something, the friction will be more. It is lesser in the kind of concrete roads. Let's say most of the places they also use that. And actually, so in countries where a lot of ice is there, in winters, they have a problem of negative rolling friction force. So you don't have any friction because a lot of ice on the road, and it's basically a disadvantage there. It's not advantages. So in this case, the formula is the rolling resistance coefficient into the weight into the cos theta, if there is any slope involved. But if it's a plain road, this cos theta will be 1. Okay, so basically, so if you are on a concrete road, you have the least mu error. On a gravel, it is slightly higher. Tar road, it is slightly higher, and if you are in a mud and all that, it will be very high. So let's say typically, so the wheels on rails, so they are very, very low, because so it's so that's why the trains don't face this rolling resistance losses. These are empirical formula. Okay. So this gradient force is basically this mg sine theta if you are going up a hill. So theta can be positive, theta can be negative. So when the theta is negative, basically you have to break the system, and this breaking energy you can recover also as a regenerative power if you operate the electric motor as a generator. So that is this is disadvantage to some extent, but is advantageous when you are coming downhill. But this is very very, very heavy force. So electric vehicle cannot go lot of theta. Basically, electric vehicle designed for a flat road are designed for a maximum theta. They are designed for maximum theta of 6 degrees to 8 degrees. That's all. If you use those vehicle for very high theta, basically it may give problems. So that has to be checked. So it can this force can be positive and it can be negative. The negative energy can be recovered using regenerative braking. So there are 3 forces. So you have seen, right? So 3 forces. But let's say there are regulation agencies like ARAI. So Automotive Research Association of India, that's in Pune. So that is a organization which gives certificates to all vehicles, whether it's a petrol vehicle, diesel vehicle, or electric vehicle. So these are the agencies, right? So they don't, go too much into this mu RR, CD, or all these things. They don't go. They will just tell you. Let's say if you take your vehicle to those regulation agencies, they will just give ABC. They will do some tests, and they will give, based on this formula, they will give the ABC constants for your vehicle. Okay. So actually now we have to understand, okay, A means some kind of road resistance, B means some kind of the inertial losses, and this means, okay, aerodynamic plate is proportional, but it is not going to nitty gritty of the. So at some ambient conditions, these are the ABC parameters of the vehicle, and they can also give the plot. So if ABC variation with respect to climate conditions or road conditions, they can also give that those kind of plot, but they don't go to specific things. So these parameters are found by some kind of test which is known as coast down tests. So basically it's kind of de-acceleration test what we do in our lab for measuring the inertia of the motor, right? But so in the electrical machine lab, if you want to measure the inertia, the mechanical friction, or the other kind of frictions, what we do, we operate the system, let's say at no load, and we'll try to find the losses, right? So those so electrical power input to mechanical losses are mostly in friction. So we find the mechanical friction time constant. And how to find J? So J we find, like, we run the motor to certain speed, and then we'll remove the electrical excitation. So motor will slowly the speed will come down to 0. So so that basically when the mechanical system speed comes, let's say if you run at certain speed and remove any input power, it will come down to 0 using a mechanical time constant. So that is generally J by B, or inertia by. So once you know the B in advance, if you know that TM, mechanical time constant, you can find out what is the J. So like, this is very similar to this. So vehicle is allowed to coast down at 130 km/h in neutral, and then they find out how these all things are vary as a function of constant with respect to velocity and velocity square. So it can be, you can do some kind of curve fitting and all that. Yeah, gradability. Gradability is very important term. So it is actually, it tells you what kind of slope you can go. Let's say when you have designed a vehicle, already the vehicle is designed and everything is there. You have used a motor of particular type, particular rating, particular torque rating, speed rating. You can tell what maximum slope it can go. So, and gradability, actually it will be there in your brochure of the if you buy any thing, you will, if you buy any vehicle, in the brochure it will be mentioned. Okay, going ahead. So basically, how do we find that? So let's say FT is the the available torque, maximum torque force what we available from the motor. So motor is a particular torque rating, and if you use the gear ratio, you can find the torque what is available on the wheels. So that wheels, if you divide by the radius of the tires, you get the force. So, and this force you to substitute again mg sin theta. So using that, so this is known from the motor rating and the gear ratio, and we know the weight, g we know. So we can find out this theta. So the gradability is calculated as the ratio of rise to run, tangent of the slope angle. So it's a kind of that. So so generally, if you see the percentage grade slope of 45 is 100%, but 6 is 10.5. So generally, this actually electric vehicles are generally designed for grade of 6 or 8, not more than that, because if you allow more slope to be covered, the we'll check about, and you can check in a simulation that the size or the power rating of the motor becomes very high, and so so generally. So this accelerating force. So accelerating force is our requirement. So it is not opposition force, but let's say we want to accelerate our vehicle at certain acceleration and dv by dt. So this is our requirement. So this also has to be supported by motor, right? Who will give the torque? So torque, what is coming from the motor is serving acceleration demand and the resistive forces demand. So actually, so there are a lot of rotating components in the vehicle. So basically, there's equivalent, torque because of the rotating parts. So generally, they are also added in the this linear acceleration. So there's a torque with respect to the angular acceleration also. So this is the thing, right? So what is the total tractive force required? It has to support rolling resistance, gradient, aerodynamic drag, linear acceleration, and angular acceleration. So if you write all together, it will be like this. And you can also write those things as a function of ABC constants also. Mr. Singh, I hope no noise is coming. Hello?
No problem, sir. We are focused on you, sir.
So something is going on. Yeah.
No problem, sir. No problem.
Actually, I can come to this the speaker also if you want. Come back to speaker. So in motoring, actually, so this is a system, right? Let's say you have an energy source, which is battery. You have a power converter, electric motor. Then you have a gear, and which is going to a differential system. And differential is connected to two wheels. It can be a front-driven wheels, or it can be a rear-driven wheels. So this is a system. So basically, as I told you, the speed in the axle will be generally at the order of few hundreds, roughly 100, 200, 300 maximum. So, but we use generally motors which are 1500 RPM, 3000 RPM. So you require a gear ratio here. So it's a speed reduction and torque increment. So if speed is reduced, the torque will be more in the wheels because the power has to be constant, right? On the either side of the gears. So in the motoring, while doing the motoring operation, generally the power is coming from the battery to the wheels. But on the other side, if you are you are going downhill, or let's say if you are going at high speed and you want to stop your vehicle, you need to apply brakes. So rather than applying a mechanical braking, you apply electrical braking. So if you pull out the power from the motor by providing a negative, you reverse the direction of current, it will automatically ask power from the mechanical systems back to the electrical motor, which is now a generator, and it can, this is to be bidirectional converter. So it should be capable of recovering the energy and putting to battery. So actually, this simulation is basically, this talk is a mix of modeling and simulation. So let's say if you want to simulate this kind of system, let's say we can take so if you take any book on electric vehicle or something, you will find some typical numbers. So let's say the mass is 1500 kgs, mu r is 0.01, CD is 0.26. Frontal area is a good number. Let's say if you have a theta is 0 and the rho is normal. And if you, so let's say you actually your wish is you want to drive at 40 kilometer per hour. Okay. So if you drive 40 kilometers per hour, all these forces, this PG, PR, this can be plotted as a function because they're a function of velocity, right? So I'm talking about steady state. So if the theta is 0, your the gradient is 0. But your aerodynamic drag, you can see this yellow line. So it is increasing as a Q function of speed. So it is becoming very high at very high speed. The rolling resistance, is increasing kind of gradually because it is so this is power. So basically that force is constant mu r mg cos theta and into velocity. So this is just a linear function of velocity. So if you add all these three together, this blue one, orange and yellow, this is the tractive effort what is required to be met by your electric motor. So the motor power rating is 12 kilowatt. Okay, at if you want to drive at 100 kilometer per hour. If you want to drive at 50 kilometer per hour, the same motor rating comes down to 4 or even lesser than that, right? So you can see that if you want to, very high speed operation or something, the size of motor can become, 3 times. So basically, and also, these forces also has to be minimized as much as possible by decreasing the drag coefficient, frontal area, mu r and all those things. So actually here the range versus the performance is playing. Okay, this is what we have even seen in one of the examples. It's like just if you just discuss only about aerodynamic drag, then if you just want to increase the, let's say increase, no, if there's a wind and there's no wind. So if there is a wind, so if there's no wind, you want 8 kilowatt. If there is a wind of 10 kilometer, you want around 10 kilowatt. So 2 kilowatt more you want. So at 100 kilometers, of course, actually. Let us see how this this drag coefficient. We see the design of the vehicle is important. So if it varies from 0.26 to 0.4, this is a huge change. So this is what I was saying that let's say many people think that they can convert the existing vehicle. You take a old diesel or petrol vehicle and convert it to electric. It can be done. There is no problem in that. But your system is not the your system was not designed for, so petrol systems, petrol based or IC engine based systems are not designed aerodynamically, and that they also don't worry too much about weight and all those things. So basically it's not a good idea. You can design it, you can use your vehicle, but your range and performance will be highly sacrificed. This is the same thing what I plotted earlier also. Here I wanted to show, I think, something. Yeah, the effect of theta. So this is for 0 theta. So if this is 0 theta, this is the thing. If there's a theta of 3 degrees, then this gradient force will start coming into picture. So okay. So here the total power is 12 kilowatt. Gradient is 0. Let's say 100. This aerodynamic drag is 8. This is 4 plus 8 is 12. If you just make a theta of 3 degrees, your gradient force itself is 20. Can you believe it? And your total power will go up to 35. just you want to drive continuously at theta at 100 kilometer but at a theta of, so if there's elevation, actually you should basically decrease your speed. We always do that, but I just want to show you the effect. Basically, if you want to keep the same power rating, let's say if you want to keep this 12, so you basically, if you there's a theta of 3 degrees, you should reduce the vehicle speed to 40. Because if you are using a motor of 12 kilowatt or something, right? If you're designed for theta 0, you can maximum go at 40 kilometer per hour. You cannot go more than that. On the on the positive side for EVs, actually EV loves negative gradient. So if you have a negative gradient, this FG will be negative power. Negative power means you are basically gaining the power from the mechanical system, because the potential energy you are gaining. Because here the potential energy is killing your system, but here potential energy is helping you. So you can see that even though these other two forces are positive, because they have to be positive because running at positive speed, but let's say if you are coming down a hill with negative 3 degrees and you are running still at 100 kilometer, you can actually recover. You will be recovering 10 kilowatt. So okay, I think maybe I'll just go to some simulations. Basically, today I was seeing. Okay, so basically, these simulations what I have shown you now, right? I've shown you this kind of simulation. So these are plotted in MATLAB only, right? So you can just write a M file program. Okay, so just try give a gear ratio. Radius of the wheels, mu RR, CD, these all parameters you add, efficiency of the gear, rho, Tmax. Tmax basically, let's say here we are telling that we have a motor which has a maximum torque of 40 Newton meter. Okay. And let's say we have no wind or no theta. So if we are using this kind of vehicle and we operate all the torque right from starting, what will happen? Let's say you have you have pressed your accelerator of your electric vehicle to full. We're continuously pressing from starting. Your vehicle is at rest, 0 speed, and you accelerated. You are in a let's say you are in a expressway where you can afford to do that. You pressed your accelerator to full, then what will happen? So what is it will tell you the performance of the system. So this is an important basically thing. So actually, basically here, so what will happen? Actually, the speed will increase, and let me run and I will show you some graphs. So probably it is there in my simulation also. This. Okay, later it is there. Okay, anyway, I can show it now also. So if you do that, this is the performance. So if you have a system with those kind of mechanical parameters, and you have a motor which is, the torque rating is 40 Newton meter, and if you just press the accelerator, what will happen? The speed will increase, keep on increasing, and it will settle down. So this is the maximum, the settling, so that the force is there. And that equation what we are using, right? So we were using these equations, right? So if you see this equation, so if you apply constant force here, So this will settle down, right? It will start a certain acceleration, it will settle. So there is some steady state speed it will reach, and it cannot go beyond that for that system. So this will tell you what it is. So it can go maximum speed of 250 km per hour. And the distance is also coming up. So the power, power is basically function that force into the force is constant and the velocity is increasing. So this is the power. So basically, somewhere you require the motor power rating to be somewhere around 130 kilowatt system. Basically, so the power rating of the motor will be 130 kilowatt. The torque rating should be 40 Newton meter. Then only for this mechanical system it can go to this speed. So here you can play, right? You can play that, okay, I don't want to go to 250. I want to go to 100, or I want to go to 150. Okay, if you want to go to 150, definitely the power required is I don't know how to see that. So you may require the motor of only 78 kilowatt. So actually, this kind of analysis can be done. This is what is called iteration. Okay. So this is another way of seeing the system. So this is it's what I wanted to talk also. So. Okay, so actually another thing we can see, let's say, what I will do, I will replot it for a theta of, let's say, 3 degrees, okay. For a 3 degrees, okay, let me do that and let me replot. Okay, so can you see this, so what has happened actually? Yeah, if you have increased this rate for the same motor, since you have introduced a slope, your maximum speed is not 250. It is now maybe 220 or something. Okay. So, so you're basically, for the same system, you want to go to some slope, so your performance is affected. Naturally, here the acceleration is much better. Actually, we all want, high acceleration. Acceleration is another important parameter. See, the acceleration is an important parameter. So let's say if you, how soon you're able to go to 100, let's say in some, this is, earlier you were able to go in 13 seconds. Now you are going, now you are going at roughly 20. So basically this is a thing, right? So if you still want to get this kind of performance here, then the power rating has to be quite high. So it's this kind of interesting simulations can be done. Okay. So basically, these are some calculations which I was already discussing with you. Basically, so this is the wheel, which this is the wheels of the vehicle. So radius r. So efficiency of the gear is important. So so generally we know the velocity of the wheels we already know. Like we know velocity or acceleration, dv by dt or v. So once we know the things here, we can understand what is the motor torque and motor omega. So once this so omega w is the wheel. So let's say this is the wheel velocity. So what is the wheel angular velocity? It is v by r, and the angular velocity at the wheels is gear ratio into this. Similarly, let's say you want so once we know the force what is need to be applied, so so this force depends on v dv by dt plus all this position and all these things. They will tell you the FTE. From FTE you can calculate the torque on the wheels, and torque on the motor can be using this gear ratio and the efficiency. So this can be the reverse calculation. So this is we are writing in so this the force equation we already know. So this force equation we can convert to this motor equation. Okay. So this velocity is still the wheel velocity, but I'm converting back. We are converting back this Ft to torque of the wheels and the torque on the motor. So so for this velocity performance and this dv by dt performance, what is the motor torque? We can calculate, right? Or another way is like for a fixed TM, what is the performance? So either way we can do that. Either we should give this as input, we can find out this. We can a second way is like we can give this parameter as a constant, we can find out the. So that's what we have done some time back. So basically this can be written as this kind of equation. Just a minute, I am coming. Yeah, sorry, I'm back. So,
Yeah, no issues, sir.
so, so this equation we are able to write in terms of d by dt. So this is a kind of dynamic equation. So okay, so basically another way I wanted to, so there are two ways, right? Either you give a force and calculate the performance, that what we have seen some time back. But another way is like, it is not the way we operate the system, right? How we operate our car. Let's say we go out of our car and take on the road. Sometimes we accelerate, sometimes we brake, sometimes we go to constant speed. It is not in our hand, right? It is relating to the conditions of the traffic and all that. So actually, we give somewhere, somewhere we ramp the speed, somewhere we run at constant speed, somewhere we give negative d by dt, or somewhere we just go to neutral, right? We go to high speed and then remove the acceleration. So a lot of these things so actually this is not the way we actually operate. Actually, let's say if the traffic conditions are in our hand, let's say if you're going in the morning or if there's a clear road, then what we will do, let's say we have to go to on expressway. So what we will do, let's say we want to go from one city to another city in expressway. So we will like to go as far as possible. That's what we want. Like we always are, short of time generally. So actually, young people actually they want to go as fast as possible. The more young the person is, the less time he has, and so okay. This is on the lighter side. So let's say we want to go from one city to another city, and expressway is there. There is no problem of traffic and all that. So what we'll do? We will go with a maximum acceleration starting, because we should. Let's say if a motor of some power rating, and some torque rating, we will apply maximum acceleration, and and we'll allow the motor speed to go. So we have seen that, right? So we have seen this thing, right? Where it is? It is here. So we have seen that if you just put the acceleration, the speed will go, and it will go to some. This is the maximum speed. It will go, and you cannot go more than that. Right? But what should be the design? Should we design this motor at this? Let's say if you take the blue curve, should we design the motor at 120 kilowatt motor? If we want this performance, let's say we want our maximum speed is 250. Okay, that's fine. But do we want to go to 250 at all? That's the fastest acceleration we want to go, or we will say that okay, I want to go only 100 at fast, and after that I can go slower. Let's say if somebody tells that I want to go at this acceleration only up to 100 km/h, but after that I am ready to sacrifice my speed, sacrifice my acceleration. Sorry, maximum speed will be like this, but will be 250 only. But I don't want to go at this acceleration. I am ready to go at slower acceleration. Then what will happen? You don't require much torque. So you can say that you want full torque here, but you're ready to sacrifice your torque here. So that is what we know as constant power region. So we should not design the machine like this. We should design the machine somewhere here. So machine should not be designed for 120. It should be designed somewhere around 50-60 kilowatt, such that your initial performance is as it is, but after that the performance, you are ready to sacrifice the performance at the cost of motor rating and the motor cost. So that's what we want. So that is how it is designed. You should not design like this. This is not a good way of design. That's what I want to discuss here. Oh, okay. So we, rather than always operating in constant torque, we design the machine such that the size of the motor is less and the weight is less and all that cost is less. We require we design it torque of the motor is such that torque and the power it is such that our initial performance is good, but after that I don't want to increase my power anymore. So here I am telling that I will use the motor which is let's say 70 kilowatt. 70 kilowatt motor I will use for this application. So if you use 70 kilowatt, what will happen? You cannot, what will happen at this speed? Your power will be reached. You don't have any more power. You don't have this power available to you. You have only 70 kilowatt. Then what will happen? So because you have 70 kilowatt, this speed will become slower. That is okay for you. So that's why these three regions are important. So I will explain those regions. So how the motor is designed like that. So this is a speed. Okay, this is a speed so axis speed, and here we are plotting torque and power. So what we do, we apply, this is the rated torque of the machine. So rated torque we apply initially, speed will increase, and when it reaches this this rated speed, this rated speed in rated torque is rated power, right? You all know. So this is the the machine design. Rated torque, rated power, rated speed, we fix it. So this is the rated power. So up to this time, the acceleration will be very good because you are applying maximum torque. But after this, your machine power is saturated. You can't, you don't have any more power to accelerate. So the acceleration what you achieved here is not more possible anymore. So what you will do without, so what you will do, your power is constant because this is the power rating of the machine. So this torque into speed is power. So torque is constant, speed is increasing linearly, so power is also increasing linearly. So here you reach the rated power. But still you want to increase the speed. Okay, you want to increase the speed is okay. But you cannot violate the power. So what you will do, you will not, your speed, you still want to increase the speed, right? So the rated power divided by whatever speed you want to increase, you will decrease your torque, such that the new speed and the torque is equal to the rated power. So here what happens, your torque is started decreasing because you have wished to increase the speed. Because of that, the acceleration will become slower here. Because acceleration depends on the torque. So this is how we operate the system. And somewhere here, you have reached maximum speed. When you reach maximum speed, you maintain this torque. That's all. Okay. So can you understand, right? Can you appreciate this? We have designed only motor for 70 km/h. We are still going to higher speed, but at reduced performance after rated speed. That should be fine, but the motor rating is drastically reduced. So pertaining to this, and then here there are three modes of operation: constant torque, constant power, and there is something called constant speed. Constant speed means so you have reached 150 and then you can float at 150, right? In expressway you are going, you have reached a speed of let's say 50 km/h very fast. Then from 50 to 150 at slightly slower acceleration. At 150 you are floating. That's the maximum speed you are operating. So depending on these three regions, the equations will be slightly different. So in constant torque mode, you have to use the first thing, right? Where this M is T max, and you find out the performance, right? So this is the what we have simulations we have seen, right? So this constant torque, the initial understanding is correct. So this is the equation of the system. In constant power region, your torque is not T max. Torque is P rated by velocity, right? It is P rated by, so such that your torque is not constant. It is decreasing as a function of speed. So it was T rated when this was V rated. So P rated by V rated is a T rated. But once you have reached V rated, if you want to increase V more than V rated, so here basically you can say that when you want speed, basically desired better than V rated, then you go to this operation, and so here your torque will be inversely proportional to torque will be 1 by V. So this is what happens here. So this is okay. So this is how you design. Otherwise, you have to design a very high. If you want full constant torque mode, then the size of the. So that was right. Basically, the fight between different high-end vehicles. Somebody will tell, okay, I can go to 250 and I can go 250 in. So here time is not so time. So this somebody can go. I can go in some seconds. Then somebody will use a higher motor. So this system will go at 150 seconds. But if you use a low power motor, let's say if I so this is the performance of the system when okay, let me I think just do quickly. So I will just stop this and I will just do that. Okay, this is let it be 0. So let's say so here the motor this 40 Newton meter and this is the thing, right? So so this is the performance. Okay. Now, so we told that we will use now. So we actually here I'm telling that here the motor power rating is 150. If I'm telling that we will use only 70 kilometer power rating. Oh, this is in kilometer. Okay, I think I should do. Okay, I cannot tell here. Maybe I can tell using. I think proportionally I can do that. Yeah, if you use less power rating motor, you cannot even reach this 250. Yeah. So no, you can reach, but actually we are affecting the torque. We should without discuss. What we should do is without decreasing this, we should decrease the power rating. So we should limit limit this, I think all of you can understand what I'm taking. So we should use a motor. So automatically, if you use a motor, your performance, you can still reach 250, but not at the that I think we'll see in the next simulation. No problem. So I think this simulation we are not. So basically, these equations will become different in constant torque, constant power, and constant speed mode. See, there is no acceleration, right? In constant speed mode, we are not accelerating anymore. So this dv by dt term is not there. So what torque you want is still, it will be constant. Only it will support losses. So only losses has to be supported in the constant. So basically, if you see this curve, so this torque actually here acceleration is still happening. But after that, since the dv by dt is term, so this torque will not be this also. It will come down. It will come down very low. So this we'll see. Okay, so okay, Dr. Singh, I think it's only 11:30. So shall we take a break or something?
Sir, it depends on you, sir. No issue. We can take a break also, and we can continue also, sir. Sir, what do you say, sir?
Okay, nice. I'm okay. 1 minute. So I can continue for still 15 minutes. Then we'll take a break.
Yeah, no problem, sir.
Okay. No participant is speaking. So basically, it's also possible, to do some kind of simplification. Actually, I have not explained this, but anyway, so this is what we have shown earlier also. Yeah. So this is what I wanted to show. See, so here, you can see that the acceleration is faster. Then the acceleration has become slower, and then here acceleration, there's no acceleration. So this is kind of constant torque region, constant power region, and so if you up to, so this is constant torque, constant power, right? So so here actually velocity with respect to time, you cannot see that what is happening. So but if you go the next slide here, so this is where the torque is operated. So torque is constant up to. So this is the power rating of the machine. This torque and this speed. So this is roughly let's say 13, and 13 means, so power rating of the machine is this velocity into this torque. Here this is the machine rating, and now when the machine rating is reached, you cannot accelerate. This straight line cannot go. So so what you will do, you will start. You will still try to accelerate, but with maintaining that power constraint. So speed is increasing, torque is decreasing, such that power is constant. So speed will increase and torque will decrease. So here speed is increasing, but at slower acceleration. And somewhere here, this is 250 is maximum. Okay, no more. We have to go. Okay, so this okay. Now I can probably explain this. I think this is the same thing. So here for 250, we required a power of 120, right? But I think for this application, what I am telling, if you do that, the power rating will be enormously low. So something like so. Okay, so here we do constant power region, and then this is the constant speed region because we don't want more than 250. So this is reduced. So anyway, this is approximation equation. So actually, it's possible to approximate these things. It's possible to calculate this time in, if you give the parameters rated such as P rated, V rated, T rated, you can calculate the time. It will be in constant torque. All these things can be calculated analytically. So I'm not going into that. So the approximate calculations are quite good. It's quite good. And similarly, this distance is also calculated. So what is distance? Distance is velocity into time. So if you do that, so you can basically calculate, what. So distance is increasing. So this is the distance in kilometers. So, so this also is important. How I is now, like somebody can ask me, what is the range of this vehicle? So how to calculate range? This is a performance we are giving. We are giving full torque, and we are using a motor of let's say this power rating, and we are giving maximum torque, and it's accelerating and going at higher speeds. But what is the range? Where will we stop? So there is another thing which we do is like we also plot energy. So what is energy? Energy is integration of power into time. So if you plot energy here, energy will also increase. So energy, you have so energy will increase, and you can see that the available energy. So you have initial energy available in the battery, and when that energy is depleted, my vehicle will stop. So where all the energy is depleted, the system will stop, and that is your distance covered. So that's how you find the range of the system. So this range calculation is equally important. So this kind of very simple MATLAB programs you can write. So here what we have done, we have written all the mechanical parameters, then we have calculated. So once we know the Tmax of the thing, we'll calculate what is the maximum torque tractive effort you can actually give to the wheels. And these are the resistive forces which are these constants. And you can write these equations, and you can plot. So these are the equations what I was talking about. So this is the equation as I was talking about, right? So in the constant, so this performance is only for constant torque region, right? So this equation was plotted. So this equation was, so this K1, K2 constant were put, and this equation was there, and so this you can write as Vn plus 1 minus Vn by T. So the Vn plus 1 is the previous velocity into this, like you can write this as a Euler form, and you can do the integration. So velocity is integration of this, right? So so this discrete equation we have written. So velocity, power, distance, P average, and P average is important. Then we can plot this, and actually it's also possible to calculate the velocity at 5 seconds. So since each time division is some seconds, 0.1 second. So at 5 seconds means let's say 500, around 400, 590, 500 points. You can calculate this. It's very so this very nice programs. Actually, I used to you can do some lot of analysis. If you have some system, and let's say you want some different performance, you play with. Okay, I don't want some number I can improve, mass I can reduce, I can improve my CD, then what it will affect. A lot of these things. So I think Dr. Singh, actually, can we stop?
Yes, sir. Yes, sir. We can take a break. So, sir, are you allowed to ask question at the moment if any participants would like to interact, or shall we do at the end?
1 minute, I'll just come.
Okay.
I can take questions 5 minutes, 10 minutes.
Okay, okay, sir. So dear participants, if you have any questions, you can ask. So I think, sir, there is no question. So, sir, we'll take a break and then we will resume it again, sir.
So we'll take a break.
Yeah, yes, sir. So how many minutes, sir, shall we take? How much time?
Uh, oh, it's a break. Okay, so what do you think? How much break is enough?
No, sir. I'm I'm confirming from you.
So we can start at 12, no problem.
12. Okay, sir. No.
We'll start at 12, and so maybe we'll wind up by 1:15 or so.
Okay, sir. That is great. Great.
Yeah,
Okay, sir. So thank you so much, sir. We will meet up again at 12.
yeah, 12 o'clock. Okay.
Yeah. So their participants will again assemble here at 12, and then sir will continue the discussion. Thank you.